This is the video for section 3.3, global optimization. So in this section, we're going to be interested in finding global or absolute extrema for a function on given intervals. So to motivate what we'll do in this section, let's look at the function f of x equals 1/3 x cubed minus x. Now, if we look at the graph of this function on the whole real line, on the interval from negative infinity to infinity, we see that f of x has a local min and a local max at -1 and 1, but there's no global extrema. There's no absolutely biggest point or absolutely smallest point on the whole graph. But notice that if we restrict our domain, say on the closed interval from -2 to 0, then we do have a global max. Namely, we have a global max at x equals -1, which was the same place we had a local max in the original function on the whole real line. And we have a global min at -2, which is one of the endpoints of our interval. So on this closed bounded interval, we do have a global max and a global min. And in fact, the extreme value theorem tells us that that is always true under one restriction. So if I have a continuous function, if f is continuous on the closed interval from a to b, then f attains its global max and its global min in the interval from a to b. So notice what the extreme value theorem tells us. It tells us that if I have a continuous function on a closed interval, I attain both an absolutely largest point on the interval and an absolutely smallest point on that interval. So in particular, it says there is some x, which I'm denoting x sub min in this interval, with f of x sub min equals little m, and such that little m is less than or equal to f of x for all the other x in this interval. So there's an absolute min in this interval. And similarly, there's another x, or maybe the same x, there's an x sub max in the closed interval from a to b with f of x sub max equal capital M, and capital M is greater than or equal to f of x for all x in the closed interval from a to b. So, in other words, there is an absolute max. And notice that if we put these two together, it gives me the following mathematically useful statement, which is that if f is continuous on the closed interval from a to b, then there are two constants, little m and capital M, such that little m is less than or equal to f of x, which is less than or equal to capital M for all x in the closed interval from a to b. And mathematicians would say, in other words, f is a bounded function. We can completely contain the function values between the lines y equals little m and y equals capital M. So we'll be interested in actually finding these global extrema. So the question we should ask ourselves is, where can global extrema on a closed interval from a to b occur? Can they occur any darn place, in which case our lives would be hard, or are there only particular places they can occur? So if you think about what we know about relative extrema, you know that relative extrema can only occur at critical points. So that is definitely somewhere that a global extrema could occur. And our first example, we saw that we had a global max at one of our critical points of our function. But if we think a bit more, we might realize that there's one other place that we could get a global extrema, and that is at the endpoints of the interval. In other words, either at x equals a or x equals b. And in that first example, you saw that we had a global min at -2, which was one of the endpoints of our interval. So these are the two places where our global extrema can occur, either at critical points or at the endpoints of our intervals. And so this gives us a very nice procedure to find our global extrema. First step, find all the critical points between a and b. If we find a critical point and it's not between a and b, it's not that it's not a critical point, it's just not relevant for finding the global extrema between a and b. Then we want to evaluate the function f at all critical points and at the endpoints of the interval. So evaluate f at all critical points between a and b and at the endpoints of the interval. And why am I evaluating f? Because I'm just interested in what the absolutely biggest function value is and the absolutely smallest function value is. So I don't need to do anything here with evaluating first derivatives or second derivatives. It's enough, since these are the only places that extrema can occur, it's enough to just check the value of the function. And the largest function value will be my global max, and the smallest function value will be my global min. So let's see an example of this. Let's find the global extrema of f of x equals 1/3 x cubed minus x on the closed interval from 0 to 3. Step 1. We want to find all the critical points that lie in our interval from 0 to 3. So I take the derivative, it's x squared minus 1. That's a perfectly continuous function, nicely differentiable everywhere as well. So we're only going to have critical points of the type f prime equals 0. So I set this function equal to 0. I factor it to x plus 1 times x minus 1. And so that tells me that my critical points are x equals 1 and x equals minus 1. And of course I just continue on from here, right? Wrong. X equals -1 is not in the interval from 0 to 3. So while it is still a critical point of the function, I just don't care about it for this problem. So x equals 1 is the only critical point I will consider because it's the only critical point in the interval from 0 to 3. Now, step 2. I want to evaluate f of x at my critical points and at my endpoints. And remember, what is underlying this is the extreme value theorem. It guarantees that I'm going to have a global max and a global min, and that these things can only occur at critical points and endpoints. So all I need to do is check the function values. I'm guaranteed to have a biggest, guaranteed to have a smallest. So I will evaluate f at my critical point at 1. So I have 1/3 times 1 cubed minus 1, which is -2/3. And then I will evaluate it at one endpoint. So f of 0 is 1/3 times 0 cubed minus 0, which is 0. And then I'll evaluate it at the other endpoint. F of 3 is 1/3 times 3 cubed minus 3, which is 6. So -2/3, that's the smallest of these three values. So my conclusion is that x equals 1 is my global minimum. 6 is my biggest value, so x equals 3 is my global max. And if I look at a graph of f of x equals 1/3 x cubed minus x on the closed interval from 0 to 3, we see indeed that the global min occurs at 1 and the global max occurs at 3. And notice also that this function is bounded between the global min value, y equals -2/3, and the global max value, y equals 6. So if I draw these horizontal lines, what do I mean by being bounded graphically? I mean that the graph of this little piece of f of x is completely contained between these two horizontal lines.